So let's learn about the atom. Anytime you see the word atomic, you probably think of like nuclear planes or nuclear weapons or the Incredible Hulk. Sorry, but atomic just means the atom. So we're going to talk about the atom today. It actually starts out about 25 centuries ago, 2,500 years ago, with the Greek guy by the name of Democritus. He believed that if you cut up an object like your pencil, you can cut it in half again, and keep cutting it up, and eventually you're going to get down to a little tiny particle, and you can't cut it up anymore. He called this an atomos, which means uncut. His argument was with another guy by the name of Plato, who basically said in modern terms, oh yeah, what holds it together, dude? And he didn't have an explanation, so Plato won. Democritus lost. Over 2,000 years later, we figured out what holds them together, and it turns out he had the right idea. They just didn't know about experimentation back then. Another Greek guy was Aristotle. Aristotle divided the world up into air, fire, earth, and water. Those are what we now call the four elements. He's also the guy who said that earth and what you call outer space are two totally different things. He divided the universe into those two things, and then the earth into these four things. But I'm telling you this because that thinking is still around today, and it's kind of cool. The old term for outer space was heaven, not in the religious sense. Aristotle talked about everything up there being the heavens and everything down here being the earth. Religions came along and said, oh, earth bad, heaven good, and we went from there. But he just divided up the universe into those things. So it's kind of neat. And we still hear talk. I mean, if I say earth, wind, fire, water, it's not out of the blue. You've heard that before. That's 2,500 years old. That's as far as they got for a long time. Over 2,200 years later, came along this guy by the name of Dalton. Dalton was kind of cool. He was a super genius, and he was real religious. He was a Quaker, and he taught in a one-room schoolhouse, kind of like you've heard of. And what I'm about to tell you made him famous, and the head science guy of Europe at the time, I don't know, came over to this backwater country, America, to meet this astounding guy who figured this out. And the story is that he finally found his way to the town, and they told him to go to the one-room schoolhouse, and he walked in and tried to introduce himself, and in that very proper English or whatever it was at the time, where they say doth and thou and all that, he scolded him for interrupting his class of mathematics and continued to teach the little kids. So quite an interesting guy. He had a theory. Okay, I'm going to stop you there. A theory is not just some unproven thing. A theory is an explanation of an observation. Observe. Pencil will fall every time. Every time means it's a law. But how do you explain how this thing falls? You know the answer is gravity, but what does that mean? Isaac Newton is the one who'd explained exactly how this pencil falls. That's called the theory of gravity. So Dalton came up with what's now called the atomic theory. There are some observations that he made, and in order to explain them, he came up with, saying it twice, the atomic theory. Some of the observations were simple. There was something called Brownian motion. When you look at little tiny things under a microscope, tiny things are constantly moving all over the place without stopping for like a long time. So he proposed that there were little tiny things, these atomos, and he was a learned person. He read about Aristotle and Democritus and all that. And he realized, hey, Democritus's idea of little tiny particles causing the bigger ones that we can see, so the smaller ones you can't see, would account for that motion. And he did a few other things that basically proved that atoms exist. Keep in mind, Democritus didn't figure this out because they didn't have, not binoculars, not telescopes, microscopes. They didn't have microscopes at the time. They just had their own eyes. So here are the basics behind Dalton's theory. One, all elements are made of atoms. These are the things Democritus was talking about. He went a little further and said that all the atoms of one element, like gold or copper or carbon, have the same mass. He said that a compound, which we already knew of, we knew about compounds, we were able to make these, were made of more than one element. To us, that's kind of a duh, water has hydrogen and oxygen. This was completely new. And he said that when they combine, they're always going to combine in the same way. So we already knew about ratios. Things like sodium chloride was a ratio, the mass ratio was always the same. There was always this much sodium and this much chlorine. He kind of gave us a hint of how things are put together. This is in the late 1700s, you know, around the time of the American Revolution, shortly after that. Well over 100 years later, scientists were messing around and they destroyed the universe. Sorry, I had to add that. Scientists were messing around and there was this little toy called a cathode ray tube. A cathode ray is this thing right here, that beam. And what they would do is they would hook up electricity to it. It could be a battery or something like that. This is, you know, they were playing with electricity back then. And they would have this little canister with a gas in it at a very low pressure, and they get this cool glowing beam. Now, it's not a lightsaber, but still, how awesome is that when there aren't even light bulbs and that sort of thing? So what Thomson did, though, is he was playing with it, and he added a positive charge and a negative charge, and the beam curved. Now, we already knew from Benjamin Franklin that like charges repel and opposite charges attract. So what Thomson figured out is that this beam right here is attracted to the positive plate. So this is a beam of something, and it has a charge, a negative charge. So he theorized, well, actually hypothesized, that atoms are made up of even smaller things, that the atom was divisible, and there were these things called electrons in it. So if electrons are negative, there must be a positive to balance it out and make it neutral. So his idea is that you've got a negatively charged particle, we now call it the electron. Atoms overall are neutral, so there has to be a positive charge in there somewhere. And lo and behold, he obviously called it the plum pudding model. Anybody British? That's plum pudding. It's a bread with raisins in it. So since we're Americans, I'm going to go ahead and give you this model here. Imagine the red stuff, the fruit of a watermelon, being positive, where you have these little tiny particles, the seeds, those are the electrons. So in the Thomson model, you have little tiny electrons, negative charge with like a haze of positive charge. That's the plum pudding model. It's a bread with raisins in it. Okay. Later, there was a guy by the name of Rutherford that did what was called the gold foil experiment because it used gold foil. And in it, he shot these alpha particles, which were known to be very, very heavy in relative terms. Kind of heavy compared to the electrons, that's for sure. Thousands of times. No, tens of thousands of times heavier. And he shot these alpha particles at gold foil. And then he had a screen around the outside to detect what would happen to the alpha particles when they bounced into the gold. Well, what he expected, alpha particles are positively charged. So he expected the alpha particles to shoot through. Now, picture the watermelon. It's like shooting bullets at a watermelon. They're not hollow point where they explode, but he expected the atoms or the alpha particles to pass through the atoms, since it's like a positive goo haze bread, watermelon. My favorite is chocolate chip cookies. That's what I would have called the model, even though they weren't invented till like the 1950s. Now I'm hungry. Rutherford expected the alpha particles to shoot through like a bullet through watermelon and really have no effect. And that's what he saw, except for the occasional one that bounced straight back. So that's like this one right here, bouncing straight back. And what he expected was totally different. After you would have thousands and thousands of particles passing through, but every once in a while one would bounce back. And he said, his quote is, that's like shooting a howitzer. A howitzer is a modern cannon used in World War I, World War II, sitting on top of a tank sort of thing. He said, that's like shooting a howitzer at a piece of paper and having the shell bounce back. There's something in the atom that's really dense. Otherwise, the bullet, the alpha particle, wouldn't bounce off it. And it seemed to, it had to be the positive charge. So what Rutherford came up with, this is 1909, this is explaining what I just said to you, is that instead of going through, they're going to bounce back. He said there has to be a tiny, compact, very dense object in the atom that holds all of the positive charge. That particle he called the nucleus. So J.J. Thomson discovered the electron. There's little tiny negative charges in the atom. Rutherford discovered the nucleus. Very dense, not very positive, just positive. Very dense, positive. I don't know if he said it was at the center of the atom, but it's definitely in there somewhere. So these guys figured out that the atom was made of smaller parts. But I want you to keep in mind that if you break the atom up even more into these nucleus and electrons, it's no longer an element. If you do this to gold atoms, they stop behaving like gold, quite literally. So saying an atom is the smallest indivisible part of an element is absolutely correct. Just know that the atom is made up of smaller parts. So today we have Rutherford's model, which is these little negative charges out here and a positive dense center in the middle called the nucleus. So electrons and nucleus. And the question is, what's between those? We'll leave that for another day. We'll start talking about atomic structure later. This is the notes for today. Thanks.